So today we're talking about the inequality side of it. So a lot of these processes are going to be the exact same as yesterday, but some of them change slightly. All right. So, and you guys can hit the light if you need to. All right. We're going to work through these examples a little bit. Now, with absolute value inequalities, there's two different ways that you can solve them. You can solve them algebraically, which some of them you have to solve algebraically. But then there's also some instances where you can solve them graphically. All right. Depending on the type of problem, graphically may be the easier way to go. So, if we're going to consider this absolute value inequality, so we're considering, the absolute value is less than or equal to 2. First off, we're going to create a number line showing all the possible solutions to this inequality. So if the absolute value is less than or equal to 2, all right, what values of x, not absolute values of x, but can someone name me just examples of x that would give us a number if we put in the absolute value symbol that would be less than or equal to 2? Just some examples. What are some values of x that could work? Say it again. 1 could work. What else? Someone else. -2 could work, because that'll give us equal to 2. We put it back in. What else? 2 could work. What else? Negative. Not quite. Think about once you put in the absolute value symbol. -1 could work. What else? There's one more. 0. So these are really the only 5 solutions that could work. Now, Corey said -3 earlier. Why would -3 not work? Right, because when you put, and not bashing on Corey, but it's a good example to talk about. So the reason -3 would not work if we plug it in for x is because, remember, you got to also take the absolute value of that x. And remember, absolute value makes that number positive. So that -3 within the absolute value symbol would become +3, which we know to be bigger than 2. All right. So again, not bashing on you, Corey, but it is a good kind of example to talk about. All right. So on a number line, we're going to kind of look at where these numbers fall. So we have -2, -1, 0, 1, and 2. These are our values that work. Now, could numbers between, like decimals between those 5 numbers, work as well? Like, for example, would 0.5 work? Yes. Would -1.25 work? Yeah. So basically, we're saying that any number in between -2 and 2 could work. And on top of that, not only any number between -2 and 2, but -2 and 2 themselves could work. All right. So how do you think we would write our answer if we were solving this? So how would we write a compound inequality to show what's going on here? And by compound inequality, I mean we got like x, and then there's less than, and you could write equal to signs if need be. How would we write it? We're basically stating what 2 numbers our solution set is between. Well, what 2 numbers is it between? -2 and 2. So these are between -2 and 2. And since it could also be equal to -2 and 2, we'll change these less thans to less than or equal to. So by writing this compound inequality, we're saying that it could either be equal to the -2 or it could either be equal to +2, but it has to be between those 2 numbers. So what we're going to do now is solve this inequality using pretty much the same process. So what we're going to do is we're going to take the x in this compound inequality and we're going to plug in the x minus 3 in place of x and then solve for x. So in other words, we have negative 2 is less than or equal to x minus 3 is less than or equal to 2. So recall solving equations yesterday. What was the biggest thing that you had to do to kind of get rid of the absolute value when you were solving equations yesterday? So for example, if I had the absolute value of x minus 3 is equal to 2. So if I just had the absolute value of x minus 3 is equal to 2, how would you solve that equation? Not quite yet. What was the step that we had to do before we could start moving things? How do we get rid of the absolute value? Nope. So guys, look back at your notes from yesterday. How do we get rid of the absolute value? Right. We had to split it up into two separate equations. Because remember, what's inside the absolute value could be equal to the positive version of 2 or the negative version of 2. Because the absolute value of 2 is 2, but the absolute value of negative 2 is also 2. So we would have to separate the absolute value equation into two separate equations, one with the positive, one with the negative. We're essentially doing the exact same thing for letter C. Because remember, it says less than 2. Well, we still got to separate it so that we have a negative version of that number on one side and the positive version of that number on the other side. Now, because it says less than or equal to, all right, and we kind of mapped out where our solutions would be. So between negative 2 and 2, that's why we make it as a compound inequality. Excuse me. Now, the next part, we'll talk about what happens with greater than, but just know for less than, this is really how you would set up your problem once you get the absolute value symbol by itself for a less than. You'd make it into a compound inequality with the lower side on one side, the lower number on one side, the higher number on the other. And then you would solve. So essentially, you would add 3 to all three sides of the inequalities. So that would go away, and you would be left with 1 is less than or equal to x, which is less than or equal to 5. So that means that any number between 1 and 5, we could plug in for x, and we would end up with a number less than 2 if we took the absolute value of that number. So let's just check ourselves. What's 1 minus 3? Negative 2. What's the absolute value of negative 2? 2. Is it true that 2 is less than or equal to 2? Yes, so that works. Name another number between 1 and 5. Just any number. 4. So plug in 4 for x. What's 4 minus 3? 1. What's the absolute value of 1? 1. Is it true that 1 is less than or equal to 2? Yes, so it works. That's essentially what we're finding. We're trying to find, with inequalities, there's no definite answer. It's a range of answers that could work. All right, that's what it means by an inequality. We have a solution set or a list of numbers that could work, not just a single solution. Does that make sense? Kind of, sort of, maybe? All right, so this would have been the answer to that inequality. That's how you would write it. 1 is less than or equal to x, which is less than or equal to 5. And again, if we stated that in words, we're saying that x is between or equal to 1 and 5. So in other words, x can be between or equal to 1 and 5 in order for it to work. So letter D we basically did with letter C. But on top of letter C, let's also graph this on a number line. So recall back to math 2 and math 1. I'm going to write my two numbers, 1 and 5. Now, we're looking for where stuff overlaps. First off, if 1 is less than or equal to x, so in other words, if we wrote it backwards, so if I separate these two inequalities into two different inequalities, I would have 1 is less than or equal to x, which is the same as what? If I wrote x first. So if I wanted to rewrite that inequality but with x first, what would be the same inequality? So x and then 1, but what symbol would go between them? So guys, if 1 is less than or equal to x, then it could also be said that x is blank 1. Say that again? Not less than. So think about it. Think about it logically, guys. So forget the math side of things. Just think logically. If 1 is less than x, then that means that x is blank greater than or equal to 1. All right? So, guys, sometimes you can ignore the math side of things because there's a lot of logic in math. All right? If you think things about a lot, if you think about it logically, it'll kind of make a little bit more sense. All right? So sometimes just saying it out loud kind of puts it into being. All right? And then the other inequality we would have is x is less than or equal to 5. So these are the two inequalities I'm looking at. So that was just me breaking down that compound inequality that we had in part C. I just broke it apart. Now, think way back to math 1. If you have a greater than or equal to or less than or equal to sign, what type of circle would I draw on top of these? Would they be open or will they be closed? Sure. They're closed. Oops. So you might want to write this off to the side just as a reminder. When you're graphing on number lines, if you have greater than or equal to, less than or equal to, that implies a closed circle. Whereas if you have greater than or less than, that implies an open circle. So what that open circle means is that if I put an open circle on 1, that means my solution set would get infinitely close to 1. So like 1.000000001, but it would never actually be equal to 1. It would get super duper close, but it would never actually be equal to 1. Same thing with 5. If I had an open circle on 5, it would get really, really close to like 4.9999999 repeated 1,000 times over. Still would never become 5. All right. Whereas a closed circle says, okay, it actually hits this number. It is equal to this number at some point. Does that make sense? So in this case, since we have those equal to signs, they're equal to those numbers, so it's a closed circle. Now, where would I shade? Where do you think? So first off, let's just do it one at a time. If x is greater than or equal to 1, would I shade to the left of 1 or to the right of 1? So in other words, where are my values that are greater than or equal to 1? To the left of the 1 or the right of the 1 on a number line? The right. So I would shade this one to the right. What about the 5? If I'm doing x is less than or equal to 5, would I shade to the right of the 5 or the left of the 5? The left. And then where you want to shade is where they overlap. So where do they overlap? Where does those two shadings overlap? In between them. So we would shade right here. So that's how you would graph it on a number line. And you will be occasionally asked to do that. So that's why it's important that you remember this. So that is typically the process for when you have a less than or equal to. So this first example was for how to solve an absolute value inequality that is less than or equal to. That's the process. All right. Now, exercise 2, little bit different. So exercise 2, we're now looking at the absolute value of x is greater than 4. All right. So let's list some numbers that could work, just like we did in the last problem. So I can plot it, so I can plot it on the number line. So what are some possible values of x that if I plugged it into that highlighted equation would make it true? Or would make the statement true? 6 would work because the absolute value of 6 is 6. 6 is greater than 4. What else? 5. Someone else. And again, we're just listing examples. These aren't the actual answers. We're just listing some sample answers. -6 could work. What else? -5 can work. What else? Let's get one more number. 7 could work. All right. Now, in this case, there are a lot more numbers. There's actually an infinite amount of numbers that could work for this one. And you'll see why in a second. But those are just some examples. So let's graph these examples. So I'm still going to have a -4 and a 4. Why would -4 and 4 not work? So if I plug in -4 and 4 in for x, why would that not work? Landon. Because it's not equal to. So absolute value of -4 is 4, and 4 is not greater than 4. Same thing if you plug in 4 for x. Absolute value of 4 is 4, and 4 is not greater than 4. It doesn't have that equal to symbol underneath it. But we're still going to write the positive and negative of that because it's just part of the solution when you graph it. And you'll see in a second. So I'm then going to plot the other numbers that I had. So we had -5, -6, 5, 6, and 7. So the reason that I started at -4 and +4 is because that's where my circles are going to go. All right. Now, in this case, would they be open or closed circles? They'd be open because it's not equal to. So we're saying that it gets infinitesimally close to 4, but it never actually hits 4. So for example, 4.00000001 is still a valid solution for x. But 4 itself, exactly 4, is not. All right, because 4 cannot be greater than 4. It doesn't make sense. Same thing with -4. -4.000001 is still a valid solution for x, but -4 itself, or exactly -4, is not. Does that make sense? All right, now let's look at the shading. So look at where my sample answers are. Which direction do you think I'm going to shade for the -4, the left or the right? So look at where your sample answers are. So left of the -4, that's where we're going to shade. What about for the 4? And right of the 4. Now, why do I not shade between them? So between -4 and 4, why do I not shade between them? It has to be greater than 4, and obviously, if you take any of the values between -4 and 4, it would not make the statement true if you plug them in for x. So for example, if you picked 3, absolute value of 3 is 3, and it's not true that 3 is greater than 4. That's why we can't shade in between the two numbers. So now we're going to write an inequality or statement that makes this true. So what is the first inequality that I could write? There's two that we're going to write for this. What's one of them? Not quite. Or yeah, that's true. So we're going to write x is greater than 4. When in doubt, put your variable first. It just kind of makes it a little easier. So x is greater than 4 is one of them. What's the other one? Landon. Right. X is less than negative 4. Now, to combine these two statements, we put a word in between them. So there are two words in mathematics that can describe inequalities. Those two words are and or. And those can describe our solutions to what we call compound inequalities or multiple inequalities on the same number line. So let me ask you guys this. Think about what and or means just in English. When you think of and, like just the word and, what do you think of? So if I said apples and oranges, I have apples and oranges. That means that I have not two. So like, okay, let's say I was talking to somebody. So let's say I was talking to Vanessa. I said, okay, Vanessa, I have apples and oranges. And Vanessa asks, so do you have apples and oranges? And I would say that I have. So if I have apples and oranges, and Vanessa asks me, do you have apples and orange? Do you have apples or oranges? I would say that I have both. So I have both apples and oranges. However, if I say apples or oranges, I have apples or oranges. And Vanessa asked me that exact same question. Is it true that I can have both or just one of them? Or. We could have just one of them, or we could have both. All right. So again, we can write this off to the side. And in math means both. Or in math means at least one. So in other words, when we're looking in math terms, and we want kind of between. So when you also think of and, you're thinking it's between, because remember, we want an inequality, and we want to graph the inequality so that both of the statements are true. We want that overlap. Whereas or means that, okay, if we went in one direction and then we went in the other direction, as long as we pick a number in either one of those, we're in ballpark. That's where we want to be. So what word do you think I'm going to put between x is greater than 4 and x is less than 4? Got a 50-50 chance of getting it right, guys. So look at the graph. And means there's overlap. Or means that as long as we pick an x value wherever the shading is, it could be correct. Whereas and means it has to be within both shading at the same time. So what do you think I would put between those two inequalities? What word? Or. So now, from example 1, what type of statement do you think that graph would represent? So look at the shading. If I picked 1 as an x value, is that in both inequalities or just one of them? Or in other words, is that in both shadings or just one of them? It's in both. So that would be an example of an and. So in other words, and you can also write this by the ands and ors, an and graph means that you're shading between two numbers. So you're shading between two numbers, whereas an OR graph means that you're shading in the opposite direction of the numbers. But as long as your answer falls in one of those shadings, it's a true statement. So that's the difference between an AND graph and an OR graph. And that's also how you can tell what word to use between them. Now, AND graphs you can just write as compound inequalities like we did up top. But for OR graphs like we have here, this is how you would write your answer. X is greater than 4, or, so we're saying X can be greater than 4, or X can be less than -4, and it makes our statement true. Whereas up top, if I stated this statement, I'm saying that X has to be greater than or equal to -2, and X also has to be less than or equal to 2. They have to hit both conditions in order to be true. Or in other words, they're between the two numbers. Does that kind of make sense? Kind of sort of maybe? All right. So now we're going to take what we just did and we're going to solve this inequality. So look at how I wrote my answer up here. So look at how I wrote my answer up here for when the absolute value of X is greater than 4. How do you think I'm going to set up the two different inequalities? So I'm going to have an X plus 2, and we're going to write another X plus 2. And then we know we're going to have a positive and a negative. So we know we're going to have a 4 here and the -4 here. What symbol do you think goes between the X plus 2 and the 4? What symbol was between them in the previous example? A greater than. What about X plus 2 and -4? What goes between them? Less than. And then we have an or in between. So that's the process for a greater than problem. For a greater than problem, you take whatever the positive number is that it's equal to on the other side, and you write that with the original symbol. Then you take the negative of that number, but write it with the opposite symbol. But that's only for greater than, so you write that with a less than. Because again, we want a graph that's going in opposite directions. All right, so that's why we do it. And then we can just solve. So to solve for both of these, I'm just going to subtract both by 2 to both sides. So that goes away, that goes away. X is greater than 2, or X is less than -6. And that would be how we wrote our answer. And then if we graphed it on a number line, so I have 2 here and -6 here. What type of circles will be on top of those two numbers, open or closed? Open, because there's no equal to symbol. Now, for X is greater than 2, would I shade to the left of the 2 or to the right of the 2? So with numbers for X, if I input them in for X, would they make the statement true X is greater than 2 if they're numbers to the left of the 2 or to the right of the 2? Which numbers would work? So ask yourself. 1 is to the left of 2. So if I plug in 1 in for X and X is greater than 2, would that work? Yes or no? Is it true that 1 is greater than 2? No. So to the left of 2 doesn't work. But then to the right of 2, 3 is a number to the right of 2 on a number line. So is it true that 3 is greater than 2? Yes. So we shade to the right. So guys, if you have issues figuring out where you shade, just go one number on either side and ask yourself, okay, does this number make the statement true? Or does this number make the statement true? Whichever one's true, that's the side you shade on. What about for -6? If X is less than -6, Would I shade to the left of -6 or to the right of -6? The left. Because the numbers to the left of -6 make that statement true. So this example, so for these two examples, all right, this was for when you have, the first example was when you have less than, all right? And all it is that if you have the absolute value of x is less than or equal to, it doesn't matter, as long as it's some version of less than, some number, that means that the way you would set up your equation, if the absolute value symbol is isolated, you'll set up the equation as the negative version of the number is less than x, which is less than the positive version of the number, and solve. So that's for less than or equal to. Whereas for greater than, if you had the absolute value of x is greater than some number, the way you would set up your two equations, as long as the absolute value symbol is isolated, is that you would have x is greater than the positive version of the number, or x is less than the negative version of the number. And then you would solve the inequalities. All right. So just remember that less than is an and statement and greater than is an or statement, if that helps you remember it. I know that's a lot and it can get confusing. And your graphic organizer is kind of a good reminder on that. Yes. Yeah. So guys, if you look at the back page of that green graphic organizer I gave you yesterday, it spells out the rules of what you're looking for. All right, it literally spells them out. Exactly. So my suggestion to you is have that on your desk while you're doing these, because it'll help you kind of remember what you got to make negative, what you got to make less than, what you got to make greater than, because it is a lot. They can get tricky. All right, so let's do these two examples together. All right, let's do letter A together. So I got the absolute value of 2x minus 1 is greater than or equal to 11. So first off, if I have greater than or equal to, will I end up with an and statement or an or statement? It's greater than. It's an or statement. So that also means that we're going to have two separate inequalities. So what's the first way I can break apart my inequality? What's one way I can break it apart into two different inequalities? Is greater than or equal to, did you say less than or? So greater than or equal to 11. That's one way. What's the other way? So it's going to involve negative 11, but how would you write it? Landon. Right. 2a minus 1 is less than or equal to negative 11. So since it's greater than, that means when I write my two equations, I'm going to basically write the original, just without the absolute value signs. And then I'm going to write it again, but I'm going to flip the sign of the inequality and flip the sign of the answer. So that's another way you can think about it. You flip the sign of the inequality and flip the sign of the answer for a greater than statement. So your first equation is just the exact same equation, just without the absolute value symbol. Your second equation, you still have the same 2x minus 1, but you flip the sign of the inequality and you flip the sign of your answer. Does that make sense? And then we just solve them separately. So they're essentially going to be the exact same process, but you'll end up with different numbers. So what's my first step to solving either one of them? Adding 1 to both sides. this will be 2x is greater than or equal to 12. 2x is less than or equal to negative 10. Then I would finish it up by dividing both sides by 2. So I get x is greater than or equal to 6, or, and don't forget to put that or, x is less than or equal to negative 5. So these are my two answers. Now, I also want to graph this on a number line. So if I graph this on a number line, so I'm just going to draw a number line, and I'm going to have negative 5 here and 6 here. What type of circles would I have on both of those solutions? So I know I'm going to have circles on top of them. Are they going to be opened or closed? Why? They're closed. Why? Yeah, that equal to underneath it. So both of these are closed circles. Now, am I going to shade to the left or to the right of negative 5? To the left, because it's less than, x is less than or equal to negative 5. I don't know why it always does that. What about for 6? Am I going to shade to the left or to the right of 6? To the right, because we want x values that are greater than or equal to 6. So that would be how I would graph it. Any questions on that one? All right, that's second example. Okay, so what did I say yesterday with solving absolute value equations? You cannot break it up into two equations until what? Maddie? Right. So we cannot break it apart into two equations until the absolute value sign is isolated and there's nothing outside of it. The same thing applies for inequalities. You cannot break it apart into your two inequalities or your one inequality, depending on the type, until you get the absolute value symbol isolated. So for this problem, even though it's less than, so first off, since it is less than, let's talk about what's going to happen. So if it's less than, what do you think is going to happen? Are we going to have two inequalities? One inequality is going to be an or statement, and statement. What do you think? So first off, and or, if it's going to be a less than. It's and. So this is going to be an and statement, which means are we going to have two separate inequalities, or are we going to have a compound inequality? A compound inequality. Or in other words, just one big inequality. All right, so that's what we're expecting to happen. But before I can separate the two, I need to get this absolute value symbol by itself on one side. So what's the first thing I need to do to isolate the absolute value symbol? We got a -3 to both sides. So 2 absolute value of x minus 4 is less than 16. And my absolute value symbol is still not isolated because I got that 2 on the outside. So how do I get rid of the 2? Divide 2 to both sides because that 2 is being multiplied to the absolute value symbol. So this goes away. I get the absolute value of x minus 4 is less than 8. Now my absolute value sign, yes, yeah. Now my absolute value sign is isolated, so I can separate it into my compound inequality. So remember, you're still going to have the x minus 4. That's going to be in the middle. All right, and then you have two less than signs on each side of that. Now, what goes on the left of x minus 4? What number? So remember, we need a positive and a negative of 8. So am I going to put positive or negative 8 on the left side here? What number goes here? Negative 8. And so the right side would be 8. So in other words, you always put the smaller number on the left, the bigger number on the right. And if you think about it numerically, that's how you would write it as well. And so now we solve for x. So what's the only thing I got to do to solve for x? We just add 4 to everything. So this 4 goes away. I get -4 is less than x, which is less than 12. And that would be how I write my answer. Now, how would I draw this on a number line? So I have a number line. I have -4 here, 12 here. First off, what type of circles do I have on both of my answers? Are they going to be open or closed? Open, because there's no equal to. Now, remember, it's an and statement. So from the previous examples, when we had a compound inequality, where do we shade? In the middle, between the two numbers. Because we're basically saying that our x value lies between -4 and 12. So we shade between the two. All right, any questions on these? All right, we're almost done, but now we kind of got some complicated. All right, so take a minute, solve exercise 4 on your own, and circle the correct graph representation. So do exercise 4 on your own, so solve it, and then circle the correct graph representation of it. So all you're doing is solving the absolute value of x minus 6 is greater than 10. And then once you solve it, circle the correct graph representation. All right, so even if you didn't get it just yet, for time's sake, we got to move on. So check your answer. So remember, since it's greater than, you're separating it into two separate inequalities. It's going to be an or statement. So you keep the original statement just without the inequality, not the inequality, without the absolute value. And then you write the x minus 6 again, but then flip the signs of both the inequality and the answer. Any questions on exercise 4? All right. Now, for this one, exercise 5, we're looking at the more graphical approach, and this is when you have some relatively difficult ones. So we're going to solve this we're going to solve this inequality by graphing because it can get very complicated because we have variables on both sides. So just like we did yesterday when we did this in Desmos, we're going to graph these two in Desmos separately. So you don't need to worry about doing this on your own. I'll do it. So in Desmos, I have y equals absolute value of, what is it, x minus 4? Right? And then y equals negative 1 half x, and then what's the other part? Plus 5. So we're graphing our two lines here. All right. Now, if we were just solving this as an equation, where would our answers be? So recall yesterday, if we were just solving it as an equation, what would you be looking for? Where the two lines what? Intersect. So here and here. All right. So I'm going to make a brief sketch of this graph. And it's not going to be exact. So I have the absolute value graph looks something like this. And then the linear graph looks something like this. And again, it's not exact. I'm just sketching it. All right. And then we had a point of intersection at negative 2, 6, and then 6, 2. So negative 2, 6, and 6, 2. Now, who recalls how you represent inequalities on graphs? So when you're graphing an inequality, not only do you graph the line, you also have to do what? Graph the shading, right? You got to shade because it goes on. So we're saying that x is equal to absolute value of x minus 4 is greater than the y is equal to negative 1x plus 5. So if we're looking at this graph, so look at our sketch. Remember, we're looking for x values. Where do you think I would shade so that my x values for my absolute value graph would be greater than my x values for my linear graph? So remember, when they're equal to each other at x is equal to negative 2 and x is equal to positive 6. All right. So negative 2 is right here and 6 is here. So we're only looking at x values. Ignore the y's. Or no, don't ignore the y's. But where on the graph are my x values for my absolute value graph, so the green graph, greater than my values for the blue graph? So in other words, what x values would make the y values of the green graph higher than the y values of the blue graph? Where would it kind of be shaded between? So guys, let's think about it. Let's just pick some random x's. Let's say x is 0. So right here it's 0. If I plug this into the first function, so y is equal to the absolute value of 0 minus 4, what's y equal to if I evaluated? What's 0 minus 4? Negative 4. And what's the absolute value of negative 4? 4. So if I graph that point, when x is 0, we get 4. So let's do this on the Desmos graph. So let's do the point 0, 4. So that's our point on the absolute value graph. Now, without even calculating the other, all right, is the y value for the blue graph bigger than the y value for the red graph when x is 0? Look where the blue line hits the y-axis, look where the red line hits the y-axis. Are the y values bigger for the blue? Yes, it is. The y value for the blue is 5. The y value for the red is 4. Well, the red graph is our absolute value graph. And we want our absolute value graph to have the greater values. So would that work right here at x is 0 for either one of them? Yes or no? No. So let's try a number that's smaller than negative 2. So let's do negative 3. So let's look at my graph, and I'm going to go graph when x is equal to negative 3. All right. So absolute value is here. The linear is here. Which one has the bigger value, the bigger y value, the red or the green? Or the red or the blue? Sorry. The red. So in other words, the red graph is our which graph? It's the absolute value graph. So is it true that in this case, the absolute value of x minus 4 is greater than negative 1/2 x plus 5? Is it true? Yes, because those y values are greater than the y value, the absolute value graph is bigger than the y value for the linear graph when x is equal to 3. All right. What about a number greater than 6? So when x is equal to 6. Well, let's do 7 because that's a number greater than 7. So which one has the bigger y value? The red or the absolute value graph? So if I were to shade this, where would I want to shade? Would I want to shade to the left of negative 2 or to the right of negative 2? So think about where 0 fell. Which one had the bigger y value, the absolute value or the linear? And think about where negative 3 fell and which one had the bigger y value. And we're looking for the absolute value to have the bigger y value. So would I shade to the left or to the right of negative 2? The left. So I would shade over here. What about 6? Would I shade to the left or the right of 6 to make the absolute value, y values, bigger than the linear ones? To the right. So if we wrote this as a solution, we would write this as x has to be less than negative 2, or x has to be greater than 6 in order for our absolute value graph to have a greater y value than our linear graph. So another way to look at it is if I'm looking at this sketch, if you notice, so you always find the points of intersection first, because that gives you like the x value, like those are your stopping points, whether you're in between them or on the same side. All right. We're looking for higher y values in the green graph, which if you look to the left of -2, the green line is higher than the blue line. So that means it has greater y values. Whereas to the right of 2, the green line is lower than the blue line. So it has lesser y values. Does that make sense? Kind of sort of what that's talking about? All right. So let's try one more example just to kind of make sure we hit home on it. So let's do letter B. All right, so we're going to do letter B. So I'm going to graph these individually. So I'm going to graph the absolute value of 2x plus 11 is equal to y. And I'm going to graph y is equal to x plus 19. So again, I'm going to graph these in Desmos. So we have the absolute value of 2x plus 11 and y equals x plus, what is it? X plus 19. All right. Now we may have to zoom the graph out a little bit. All right. So first things first, I need to know where my points of intersect are because those x values of those points are my barriers. So here and here. So at -10 and 8. So if we solve this as an equation, x would equal either -10 or 8. So that's if you solved it as an equation. Now, we're looking for where our absolute value graph is greater than our linear graph. So if we're looking at Desmos, and again, here's our point of intersections. Let's look at -10 first. So if I look at -10, this entire line, so if it helps, you can graph that line. So x equals -10. All right. So look at this line. That's your barrier line. Is my absolute value graph higher on the left side of -10 or the right side of -10 than the linear graph? On the left side. All right. Then my other barrier is at 11. Or no, it's at 8. So x equals 8. So is my absolute value graph, which is the red, higher on the left or the right side of my linear graph? It's on the right. So in other words, this is a solution when we have x is less than -10 because it's to the left of -10. So we want x values that are smaller than -10, or when x is greater than 8 because we want it to be to the right of 8. Does that kind of make more sense? Kind of, sort of, hopefully. So if it was less than, where's the absolute value graph less than the linear graph? So look at the two boundary lines. Where is it less than? Is it on opposite sides or in the middle? That the absolute value graph is lower than the linear graph. So guys, if these are my boundary lines, and I asked you to tell me when the absolute value of 2x plus 11 is less than x plus 19, you're looking for where the absolute value graph is lower than the linear graph between those two boundary lines. So where would that be? Is it on either side of them or in the middle of them? In the middle, our absolute value graph is lower than this linear graph. It's below it. Whereas the greater thans, our absolute value graph is above the linear graph. Does that make sense? Kind of, sort of? All right. you to do one of these on your own, you'd be able to do it. All right. Okay, last thing and then we're done. So some special cases. So there are some special cases with inequalities that have interesting solutions. So what did I say about yesterday when you had an absolute value statement equal to a negative number? What was it? So say I had the absolute value of x minus 2 equal to negative 5. What did I say yesterday the solution automatically is? So we don't even have to solve this because our solution would automatically be what? No solution. Why? What happens when you take the absolute value of anything? The number's positive. So is it possible to get a negative number when you take the absolute value of something? No. So this one's automatically no solution. Now, that's not necessarily true with inequalities. So depending on the situation, it could or it could not work. So we're going to do these two examples where we try it. All right. So first off, I'm going to solve this one. So it's less than. So we're looking at a compound inequality. So I would have it as 2x minus 7 less than or equal to negative 5. And then you'll put 5 on the other side. And the reason I want the negative 5 on the right is because that's how it's written originally. So then we would add 7 to both sides. This would be 12 is less than 2x, which is less than 2. Divide both sides by 2. I get 6 is less than or equal to x, less than or equal to 1. So let me ask you guys this. Is it true that x can be less than or equal to 1, but greater than or equal to 6 at the exact same time? So is it true that from left to right, your x value could be between 6 and 1? From left to right. So if you read it from left to right, is it true that between 6 and 1? No. So in this case, we have no solution because it's impossible. Because if we separate these two inequalities, that means we would have x is less than or equal to 1 and x is greater than or equal to 6. And both of these have to happen at the same time in order for it to be a solution, which is impossible. So this one is no solution. So if you see a less than or equal to a negative number and the absolute value is isolated, it's no solution, just like with equations. But now let's look at what happens when you have a greater than. All right. If we have a greater than, that means we're separating it into two separate equations. So I have 2x plus 3 is greater than the original, so negative 7. Or 2x plus 3 is less than or equal to the opposite, which is 7. So let's subtract 3, subtract 3. All right. These go away. I get 2x greater than negative 10 or 2x less than or equal to 4. So then divide by 2. X has to be greater than or equal to negative 5 or x has to be less than or equal to 2. Now, remember what an or statement is. All right. So if we graphed these two inequalities on a number line, it's easier to see on a number line. So both of these will be closed circles because they have that equal to. Now, let me ask you this. If x is greater than negative 5, am I shading to the left or the right? So x is greater than or equal to -5. Am I shading to the left or right of -5? To the right. So I'm going to shade right here. What about for 2? If x is less than or equal to 2, which way am I shading, left or right? Left. Now let me ask you this. When I say or, what did I say or means in words? So and means both, or means what? At least one. So they don't have to fit that condition at the same time. However, look at your number line. What all shaded? Is it true that everything's shaded? The entire line shaded? Whether it's going in one direction or the other? Yes. So guess what our solution is? All real numbers. That's your solution. So your solution is all real numbers. Or you can say it's infinite solutions. So all real numbers, you can also say it's infinite solutions, however you want to put it. All right. So, big takeaway. If your absolute value symbol is isolated and you have less than or equal to a negative number, it's no solution. If your absolute value is isolated and it's greater than or equal to a negative number, it's automatically infinite solutions or all real numbers. Does that make sense? So just like with the equations, you can just look at it and be like, okay, we done. Any questions on that? All right, so we're going to stop there today. We'll fill in the last little bit of your graphic organizer first thing tomorrow, but you do have enough information to at least get started on Delta Math. So, your Delta Math for today, it's a combination of lessons 1.4 through 1.6. So, you're not going to be able to get it all done, obviously. This is not going to be due until Monday. But if you look at your assignments or you look at your skills, you should be able to do everything that starts with absolute value. All right. So anywhere you see absolute value in the name of that skill, you can do it, at least today. And then we'll go through the other stuff tomorrow and Friday. All right. Yes. Yeah.
All adult notes get like overall doing
Midnight on test day. So the 11th. So if we keep the 11th at midnight.
I thought I know I heard you say that, but then you were talking about something else and it was.
So the due date that I set for the Delta Math are tentative. It's like a timeline. So I'm basically saying if you don't want to get behind, I highly recommend you do them by these dates. And I'll put the grades in then just to kind of remind you, oh crap, I need to do this. Or I already finished that one. But then you have until the test date to finish them. And then I'll go back the day after test day and regrade it. But I don't accept them past that date.
Okay, so as long as they're not in past test day.
Mm-hmm.
Okay.
And to be honest, midnight is kind of for Delta Math. I can't see when you finished a Delta Math, like what time exactly. So I mean, if it's the night of test night and you finish a Delta Math at like 1 a.m., I can't see that anyway. So it's really based off of when I open my grade book the next day, it needs to be done. You know what I mean? Now, Canvas is different. So your packet has to be submitted by midnight because it'll close at midnight. But Delta Math, I'm too lazy to set them to close. So I could set them to close, but that's too much work. So you're welcome. All right. So you guys can work on your Delta Math. You can work on packet work. Your packet work is basically finishing anything between the equation and the inequality sections. I don't know the exact pages, but I'll put the exact pages in Canvas once I figure that out, because I can't remember off the top of my head. And remember, whenever you're ready to start submitting your packet stuff, please refer to those videos on how to submit them if you don't know how to. Yeah. Yeah. And sorry that the lesson ran kind of long today. Absolute value anything always takes forever. The lesson tomorrow should not be nearly as long.